Okay. So, welcome back to the lecture series of finite volume, and this quick scheme. If you analyze the truncation error, which would turn out to be 1 by 6 del x cube minus 3 by 128 del x to the power 4 phi c 5 and so on. So, which essentially give you some sort of an third order accurate. This is third order accurate scheme. So, as we move along the hierarchical direction, second order upwind was second order accurate, quick becomes third order accurate. Now, the third point one has to check its stability. So, the stability, if you look at the right hand side convection term, this would be minus 3 by 4 phi c phi w 3 by 8 phi e m dot e 0 plus 3 by 4 phi e minus phi e by 8 3 by 8 phi c m dot e 0 minus 3 by 4 phi c minus phi e by 8 3 by 8 phi w, then 3 by 4 phi w minus w w by 8 phi c. So, to get the stability limit check, you get this right hand side term with respect to del phi c, which will turn out 3 by 8 m dot e minus 3 by 8 m dot w minus 3 by 8 m dot e plus m dot w. So, this is again less than 0. So, this shows that it is a stability stable scheme. So, if you have some sort of a uniform velocity, this will be always stable. However, this does not guarantee the solution boundedness, especially in case of non uniform velocity. So, one has to, for uniform velocity always stable, for non uniform velocity does not guarantee the boundedness. So, that is the point one has to note, that how it goes. Now, moving ahead, there is another scheme which is called Fromm scheme, FROMM, Fromm scheme. So, which is uses the linear profile between the far upwind and downwind nodes connecting the faces. So, how would that look like? If one has to put the stencil, again this is our C, this is the face, these are the downstream, this is downstream, and this is upstream UU. Across these cell faces, assuming velocity in this direction. So, what it uses some sort of an profile calculation between these points. This is phi d, phi u, and in between you have phi c and phi f. So, this is how it takes into account, and the function definition is k naught plus k 1 x minus x c, and using the value at x d and x u, which is corresponding to phi d and phi u, what you get the phi x equals to phi u plus phi d minus phi u, x d minus x u, x minus x u. That is the function that you get. Now, again one can carry out the similar exercise for this particular scheme, and what you end up getting is that now if you have this upwind node phi c, which you can calculate as phi u plus phi d minus phi u divided by x d minus x u into x c minus x c u. So, that is how you get. Now, again the assumption remains uniform grid, 1D convection diffusion system, then phi c becomes phi d plus phi u by 2, which is the centroid value becomes the average between this and this. Now, with that phi f would be phi u plus phi d minus phi u, x d minus x u, x f minus x u, which one can write phi c plus x f minus x c divided by x d minus x u multiplied with phi d minus phi u. So, you use this information here and you get this, and for the uniform grid it reduces to phi f equals to, for uniform system it reduces to phi c plus phi d minus phi u divided by 4. So, that is what you get for uniform system. So, to put this information back in the discretized equation, you calculate the mass fluxes, I mean m dot E, I mean basically fluxes at the faces, which will be phi c minus phi w plus phi E by 4 multiplied with m dot E 0 minus phi E by 4 plus phi c by 4 multiplied with m dot E 0. Similarly, you get phi w m w, which is phi c minus phi E by 4 phi w by 4 multiplied with m dot w 0 minus phi w by 4 phi c by 4 minus m w 0. So, this we are doing it for the uniform system, and then the converted discretized equation would be looking like phi c minus phi w by 4 plus phi E by 4 multiplied with m dot E 0 minus phi E by 4 plus phi c by 4 multiplied with m dot E 0, and then you get phi c phi E by 4 phi w by 4 multiplied with m dot w 0 minus phi w minus phi w by 4 plus phi c by 4 multiplied with minus m dot w, and then we have the gamma term or the diffusion term. So, this portion contributes the convection, and then this is the diffusion term by del x at w, which is phi c minus phi w equals to 0. So, eventually the equation will look like, the compact equation will look like AC phi c, AE phi e plus AW phi w, AWW phi WW plus AEE phi AE, which is 0. So, this is, I mean, the fact which remains same in the finite volume. Once you get a discretized equation, they look exactly similar for different schemes. So, if you have a one discretization in place, one can actually just using different coefficient, you have a different scheme in place. Minus 1 by 4 m dot E 0 minus m dot E 0 1 by 4 m dot W 0. Then this flux F w minus gamma w S w by del x w m dot W 0 minus minus 1 by 4 m dot 0. Now, A e, which will become flux F e 1 by 4 minus m dot E 0 A w w, which will be flux F small w w 1 by 4 m dot W 0, and finally A c, which is over the faces, flux C f, which will get you gamma E A c plus gamma W plus m dot E 0 minus 1 by 4 m dot E 0 m dot W 0 minus 1 by 4 m dot W 0, which will again remain as the summation of A e, A w, A w w, E e plus m dot E m dot W. So, these are the only places, the calculation of the coefficients, where you see the differences, and if you look at the truncation error for this form scheme, the truncation error would be order of delta x square, which also provides you second order accurate system. And the stability criteria, the stability, if you look at the convection term on the right hand side, so that will have this component phi c minus phi w by 4 plus phi e by 4 m dot E plus phi e minus phi e by 4 phi c by 4 multiplied with minus m dot E 0 minus phi c phi e by 4 phi w by 4 m dot w 0 plus phi w minus so if you take the derivative of this term with respect to phi c, which will become minus 3 by 4 m dot E 0 minus 3 by 4 m dot W 0 minus 1 by 4 m dot E plus m dot W. So, like the quick scheme, for constant velocity, this guy is always stable, and for varying velocity, this is, I mean, it does not guarantee stability all the time. It may not. So, but if you have constant on uniform velocity, this will always provide you back the stability. So, if you look at the comparison of all these profiles, so basically some sort of an comparison, if you look at various schemes, what you see is that with the most negative coefficient is associated with second order upwind scheme, that is minus 3 by 2, and then you have upwind scheme which is a minus 1, then form scheme FROMM, from scheme with minus 3 by 4, and then finally the quick which is minus 3 by 8, and CD is coefficient 0, which is sort of a neutral stability. So, the self corrective action is the sum of both convection and diffusion contribution. So, the self corrective measures comes from both the convection and diffusion contribution, and the false diffusion essentially produced by the upwind scheme, which adds to, so upwind scheme actually the false diffusion or numerical diffusion, which adds to the stability even though the coefficient is minus 1, and it is the most stable scheme amongst this all that we have discussed. So, if you put them together and plot, then you see these two curve for varying Peclet number. This is Peclet number 1 and this is Peclet number 10, and if you plot all the schemes against the exact solution or the analytical solution, so you get upwind, CD, quick, second order form. Similarly, exact numerical upwind scheme, CD scheme, quick scheme, second order upwind and form scheme. So, once you look at all the cases for Peclet number 1, which is at the low Peclet number, so you see that CD, form and quick, this guy and this guy, they basically the Peclet number 1 case, they show some sort of an wriggles here, the high Peclet number case, but in the low Peclet number case they do not show anything, but these schemes at the high Peclet number case show some wriggles, and amongst these the least accurate is the solution by the first order upwind scheme. Now, and the solution of this guy is slightly more accurate than second order upwind, and obviously it is going to be accurate than the first order upwind also. Now, when you look at this guy and this guy CD, quick and form, they show some wriggles in these locations of the solution. So, here the solution which is obtained by the first order upwind and the second order upwind, their profile being the most accurate, close to the exact solution. And now coming back to the form and quick scheme, on the other hand, they show some wriggles, but with some small amplitude, and the reason for these wriggles is that the imposed boundary condition at the exit of the domain. So, since the problem is convection dominated, it is affected by the, so these are for convection dominated flow, the solutions at the downstream is partially affected by the upstream calculations or upstream information. So, solution which are actually at the exit of the domain which was specified, this is the exit of the domain, that has some impact on these wriggles and all these things. But however, the second order upwind scheme is expected to give rise to some oscillation in the presence of high gradient in the domain if you have a shock wave or like that. So, that gives you an idea on some sort of an comparison of this. Now, moving ahead, you can actually find some functional relationship for uniform and non-uniform grids. So far our discussion was restricted to uniform grid. So, now one can find out some correlation or the mapping between uniform and non-uniform grid, and how you can do that. Essentially, let us see, if you have some sort of an element C here which will be connected with a face, this is the face F and the velocity here will be in this direction, then there is cell D, then there would be cell DD downstream, the upstream there is U, upstream UU. So, this goes in a xi direction. So, sort of an curvy linear coordinate system. So, typically my xy system or the uniform xy system, the cells would be sitting like that. This is the cell, down of that, up of that. So, this is where your uniform grid system or orthogonal grid system, and this is in the curvilinear grid system. So, one important point which is here, the functional relationship for uniform grid remain exactly same, and for the non-uniform also, independent of whether the Cartesian or the curvilinear grid system is used. For non-uniform grid, the independent variable x which is appearing in the functional form should be replaced by xi. So, what essentially it says, the functional form will not get changed, it only the notation like uniform grid use get a function with base of x, in this case it should be function of xi which will actually represent the system with the discretion. Now, if you get all this functional relationship for different scheme, then it should be put together. Let us say this is for uniform system, this is non-uniform system, then these are the scheme that we have so far have discussed. So, when you talk about the upwind scheme, this will be uniform case phi f is phi c, this case also phi f is phi c. When you talk about downwind scheme, then phi f is phi d, this case phi f is also phi d. When you talk about CD, this is phi f is 0.5 into phi c plus phi d, and this case phi f equals to phi c plus phi d minus phi c by xi d minus xi c multiplied with xi f minus xi c. When you go to second order upwind, we get phi f equals to 3 by 2 phi c minus phi u by 2. This case it would be phi f equals to phi c plus phi c minus phi u divided by xi c minus xi u multiplied with xi f minus xi c. Now, quick, you get phi f equals to 3 by 4 phi c minus phi u divided by 8 plus phi d into 3 by 8, and this case this is phi u plus you have term 1 plus term 2. We will see how they look like, and if you put from scheme, this would be phi f equals to phi c plus 1 by 4 phi d minus phi u, and this case it is phi c plus xi f minus xi c divided by xi d minus xi u multiplied with phi d minus phi u. So, you can see this difference in the functional form of this expression. Now, once for the quick, the non-uniform system, the term 1 is xi f minus xi u divided by xi d minus xi u multiplied with xi f minus xi c divided by xi d minus xi c with phi d minus phi u, and term 2 they would look like xi f minus xi u, xi c minus xi u, xi f minus xi d, xi c minus xi d, phi c minus phi u. So, where xi u is xi u u plus xi u minus xi u u, and xi u u is nothing but x u u minus x o square. So, in this particular case, this somewhere center is sitting. So, plus y u u minus y o square plus z u u minus z o square, and xi u minus xi u u equals to x u minus x u u square, y u minus y u u square, z u minus z u u square. Now, so if you put them together, xi 1 minus xi 2 is essentially x 1 minus x 2 square, y 1 minus y 2 square, z1 minus z2 square. So, this is how you can actually get the functionality between uniform and non-uniform system, and the functional form look similar, only thing the calculation of the non-uniform system, the coordinate system becomes xi system. So, we will stop here and we will continue the discussion in the next lecture. Thank you.